Okay, hi everybody. So we are going to work today on a applied problem that involves the Torricelli's law again. I really can't do a whole lot with predator-prey with you yet because we didn't really finish that conversation. I want to kind of have more debate and conversation about refining a predator-prey model, and then also recognizing that a system of Diffie-Qs is kind of in itself interesting in that you have two differential equations that you try to solve, thereby generating two different functions, and the solution to the system would naturally be the points when the rates of predator growth and the rates of prey growth kind of reach some level of equilibrium, right? So that'll be a continuation tomorrow in class. But right now, what I want you to look at is page 116, 117, number 9. And what we're going to do is just talk through this question, and we're going to work through taking a differential equation. This is Torricelli's law again, and refine it. So really, the homework entirety it's going to be question 9, question 10, and then also question 11a that kind of builds. Question 9 is a differential equation that does not take into account any kind of frictional grab of the water, the container containing the water. Number 10 then adds a refining element to the differential equation by considering a frictional constant factor. And then number 11, I believe, is a novel conical tank. So let's take a look at number 9, okay? Go ahead and read number 9. And what I like about number 9 is it kind of sets up and describes what that differential equation is, but you've seen that before. And what this differential equation describes is the rate at which the height of water in a conical tank is dropping, and as a function of height, h, right? So when you look at this model, you have dH by dt equals negative a sub h over a sub w, the root of 64h. I went ahead and put in the gravitational acceleration constant, which is 32, okay? And really, you can even refine this even more, negative a sub h over a sub w, 8 root h. So here we have the rate at which the height of water is dropping is a function of the height of water. And in this case, we're looking at a tank dripping out. A sub h is the area of the hole. A sub w is the area of the exposed water, okay, which means the circular top of the water. In the event that the tank is full, A sub w would be the area of this right here if it starts off as full, okay? So it says for part A, solve for h of t if the initial height of the water is h. So part A, the initial height of the water is h. So at t equals 0, h equals capital H was the constant. By hand, draw the solution curve and give the interval I of its definition in terms of the symbols a sub w, a sub h, and h. So we have to remember that we're treating a sub w and a sub h as constants. And what question A is asking you to do is to solve this Diffie-Q, treating a sub w and a sub h as constants, and then state the interval of definition. I'm not concerned with you drawing the solution curve by hand. No, don't do that. Just unless you really want to. You don't have to, though. I'm not. But what I'd like you to do is go ahead and solve this Diffie-Q and state the interval of definition, and then replay me if you need help or if you want to see the answer. Okay, hello. So here what I did was I separated the variables. Then I integrated both sides. Notice the plus c. Divided everything by 2, right? And when you divide a constant by 2, it's still a constant. And then I used the initial point at t equals 0, h equals capital H. So that means c equals 2 root h. And then I just subbed c back in for c, and I got h to the 1/2 equals negative 4h over a sub w times t, and then I just squared h to solve for h, okay? So there is the solution. And then what I did was interval of definition. So how do we essentially find the domain of this function, really? What is the domain of this function? Well, you know that the height of the water may only exist between 0 and capital H, right? Because capital H is, what does it say? It says that the initial height of the water is capital H. So over time, if water is leaking out, the height of the water can only be between 0 and capital H. Well, what is little h, right? Little h is right here. Here's little h. So all I'm going to do is say, okay, that means 0 is less than or equal to, okay, root h minus 4a sub h over a sub w t, all of it squared, less than or equal to capital H. I'm going to square root both sides. 0 less than or equal to root h minus 4a sub h over a sub w t less than or equal to root h. I'm going to subtract h from both sides of this compound inequality. I get negative root h less than or equal to negative 4a h over a sub w t less than or equal to 0. Now listen, divide by a negative, right? When you divide by a negative, the inequality signs are going to flip. But I'm going to divide by negative 4a sub h over a sub w. This is still 0. At the end of the day, t is between 0 and a sub w root h over a 4a sub h. This is your interval of definition. Look at that. Okay, now what I want you to do is go to 9b. So here's my hint to you. You know, you did all this work in Part A to solve a Diffie-Q. You solved a Diffie-Q and the solution is right here. This is your solution. Part B is saying, now that you've solved the Diffie-Q, how could you use this solution, this model, to answer the question in 9b? Suppose the tank is 10 feet high and has radius 2 feet, and the circular hole has radius ½ inch. If the tank is initially full, how long will it take to empty? Well, if we're going to use this model right here, I'll make some room over here. If we're going to use this model, okay, I want to know when will h equal 0. If the tank is initially full, how long will it take to empty? So what will t equal when h is equal to 0? So 0 equals the square root of, now let's see, the tank is 10 feet high and the tank is initially full. That means this capital H, by the way, stood for the initial height, right? The height of the water at time t equals 0. So root of capital H becomes radical 10 minus 4a sub h is the area of the hole. They have to be in feet though. Torricelli's law is in feet. So 1/2 of an inch for a radius. 1/2 of an inch is what? Is that 1/24th of a foot? Yeah. So pi 1/24th squared, right? That is a sub h, the area of the hole. All over the area of the water at the start. Radius is 2, so pi r squared. Pi times 2 squared, so pi times 4. All this times t squared. Now here, what I'm going to let you do is go ahead and solve this, but when you solve this, you get here, what do you get? Square root both sides. We're going to get negative radical 10 minus equals negative 1/24th squared times t, and t will equal 24 squared times root t. At the end of the day, what is this going to equal approximately? Maybe about 2,000 seconds, but this is it. You just solved, you just used the differential equation that you so arduously solved to generate the solution to this particular case. Now what I want you to do is go to number 10. And number 10, what number 10 does from number 9 is number 10 now refines the model. Okay, it refines the mathematical model. It refines the mathematical model by questioning and questioning the assumption that, you know, in this differential equation, this model here, the assumption here is that there's no friction as water leaks out. The assumption here is there's no friction. Number 10 asks, how would the model be refined if there were to be friction? If this vessel grabbed the water in a way that would slow down the rate of flow, correct? So what I'd like you to do is try number 10 on your own and see what you think. And maybe I'll do it out here. You can kind of do it out and then, or maybe I won't. I don't know. Oh, go ahead and try it on your own and we can talk about it in class tomorrow. Okay, everyone? All right, I hope that went well, and I will see you tomorrow. Have a wonderful evening. Goodbye.